Hi guys, welcome back to my YouTube channel. So in this lecture, we are going to continue our discussion on the diode current. So this is the equation that we derived last class. So if we take the forward bias, then it should be positive. Okay. So then we can consider e power v by vt, which is much greater than 1. So then we can take approximation that I, which is be approximately equal to I naught e power v by vt, right? So if it is reverse bias, then we know that v is equal to negative. So then we can take approximation v by vt will be much less than 1. So based on this, I will be proxy equal to I naught. So these two observations is very much important in order to draw a IV graph. So let's take a characteristic equation of diode, characteristic graph, IV characteristic graph. So this is one of the very important graph that we have to look. So if we take the IV characteristic, in forward bias we know that it will be an increasing exponential current, as we know that is I naught e power v by vt. But in reverse bias we know that is a constant, so that will be quite maintaining a constant value, right? So that will be most probably maintaining a constant value. So that constant can be represented like this, and then eventually it will be fading to 0. Okay, so this difference, so which is I naught, right? So this I naught is nothing but reverse saturation current. Reverse saturation current. Okay, so I hope it is understood for you guys. So based upon this observation, we can take plenty of things. Like these I naught characteristics will vary very much depending on temperature. So this I naught will be directly proportional to Ni square, that is intrinsic carrier concentration. So if T increases, Ni increases. So if Ni increases, I naught increases. If I naught increases, diode characteristic curve will increase. So let me draw a curve. So this is only in reverse bias condition, because in forward bias, the negligible small increase in this current will not be contributing much thing. So okay, here you see, this is I naught 1, which is I naught 2, which is I naught 3. Three different things. Here if we take the I naught 3 is much greater than I naught 2. I naught 2 is much greater than I naught 1. This is why, because the temperature where the diode operating at T3 will be greater than, then T3 will be greater than T1, T2. So this is because the reason for the current to increase. So if we increases the temperature, then the reverse saturation current I naught will also increases. So that's what the understanding study that we need to understand with this thing. So whenever there is a change in temperature, the thing that these current values will also be changing. So this is what the thing. So I hope it is understood for you guys. So these kind of reverse bias and forward bias characteristics will be very much contributing to everything. So we need to analyze the material in both reverse as well as forward bias. So in examination perspective, we may need to handle anything, like even in the forward direction as well as in the reverse direction. So that is what the thing that we will be majorly focusing on. So now if we know that diode is operating in forward bias, then we will be getting more current in the upcoming direction, which is exponentially increasing. But if the diode is acting in a reverse bias, then we will be getting some reverse saturation current only. That is the thing. But even if the diode is acting in a forward region or backward region, reverse region, reverse saturation or reverse bias region, there will be some kind of resistance in the diode. So we need to coin that term also, so which is diode resistance. So not all devices in the world are ideal, right? So not even a single device in the world is ideal. So everything will have some resistance capabilities. So there is two types of resistance that we can say. One is static resistance. Then another one, second term, is the dynamic resistance. Okay. So this is the static resistance offered by a diode because of DC excitation. DC excitation. The DC current when we apply, right? So that time this kind of resistance will be created. So for an example, if the diode is connected to forward bias, so this is how the diode will be. The diode physical representation will be like this. So this is P and this will be N. This is how the physical representation. Then some kind of resistance is connected here, that is R. So if we take the thing that it is connected to a voltage, positive, negative, so which is DC voltage. So if we connect a DC voltage in this, there will be some current flowing, that will be I diode. So these are DC, there will be some kind of current that is produced, some kind of resistance that is produced because of this DC excitation, that is named as VD divided by ID. So the diode cutoff voltage divided by the diode current that is produced. So because of that, there will be some kind of resistance that the material or the diode will look into the picture. Okay, so this is reciprocal of the slope of line joining the operating region. Sometimes in the graphical way also they will represent. So let me draw a graph in order to represent that thing. So we are seeing only dynamic static resistance here. So in the next slide I will discuss about dynamic resistance. So this is how the diode current will look like, right? So if there is a dynamic resistance that is acting, that will be slope, that will be 45 degree. Okay, so there will be some cutoff point. So this will be VD and this will be ID. The diode will be operating at some point. So this point, right? So this point. So this slope, this is the slope. If we take the slope, which will be equal to ID divided by VD, the y-axis divided by x-axis. So the RD, which will be reciprocal of slope. So RD, which is equal to 1 by slope. So that's what they are implying here. So this thing is only they are implying here. Okay, so this is completely static resistance. So if we need to go to the dynamic resistance, the second thing, dynamic resistance. It is because of small signal reference. So whenever we are connecting it to a AC circuit, it is because RD or RAC. So when we connect a diode to the AC circuit, then it will offer that kind of resistance. So for an example, if the diode is connected to an AC voltage, AC supply is connected, so then there will be something that will happen. The current will flow, that is be high AC. So there will be some resistance that will be acting. So where here the small amount of resistance that will act, right? So RD. So this RD will be directly depending upon the things that is happened here. So RD or RAC, we can represent as RD also. So this RD will be equal to eta VD divided by I. So this I is DC current, not a AC current. So this is a quite difference. This is DC current equation. Okay. So this is what the resistance that it will offer when it is acted on the AC current. So this thing you can remember it. So the change of di by dV because of the AC signal voltage, which will be prox equal to I divided by eta VT. So that's why this is happening. So even we can derive this one. So di by dV, which will be equal to the I equation, which will be e power V by eta VT divided by eta VT. If we differentiate this thing, we will get this one. So this can be written as I plus I naught divided by eta VT. Okay, so this is because this can be because of the saturation current ID plus as well as in the I which is flowing through the diode. So that is equal to I divided by eta VT. That will be proxy equal to I, because I naught will be very small current, right? So that's why. So how this came, this came to approximation is that, so we know that I which is equal to I naught e power V by eta VT minus 1. So which can be approximately written as I plus I naught, which will be equal to I naught e power V by eta VT. So that's what. So this is because there is a small negligible current that is taken into picture. So if we differentiate this thing, then we will get here. So this is di by dV. So then we are substituting this one here. This is written as I plus I naught. Okay. So I hope you guys able to understand the difference in that is static resistance, and dynamic resistance, that is contributor. So in the next class, let's see about how the capacitance will be coming into picture. Like there is two types of capacitance. One is because of forward junction and another one is because of reverse bias junction. So we can understand the same thing, like how the resistance is acting here. Similar to that, we will be seeing how the capacitance is acting. The simple thing is that the slope of difference between the VI curve is the reciprocal of slope is the resistance. Here also same. The slope of resistance is the slope of IV character is the 1 by slope of IV characteristics the resistance acting in this. So okay, like, share and subscribe the channel. Stay tuned guys for more lectures.